The purpose of this lab is to observe the motion of an object dropped from rest and falling somewhat slowly straight down. I chose a plastic cup dropped so that the top was facing down to satisfy the somewhat slowly requirement as my system. I then video recorded it, analyzed it in Tracker, created 2 different computational models of the cup's motion, compared their results on 2 separate graphs, and then came to the conclusion that the second model, which took into account both weight force and drag force, provided the best model. After uploading my video into Tracker, I oriented the axes so that the origin was at the center of the cup and the negative y-axis was pointing down, the direction in which the cup fell. Due to a slight tilt in the camera, I angled my axes -2 degrees from the horizontal to limit any distortion. I tracked the point mass at the center of the cup as it fell, taking the center to be the middle of the blur when blurring occurred. The following position versus time graph was produced by Tracker from the point mass data. The most important observation is that the slope of the graph is not constant and increases as time increases. We can take this to mean that the velocity of the cup was increasing as it fell. This non-constant velocity indicates that our F-net is not 0, something we have to take into account in our computational model. From my observations of the experimental data, I initially generated a computational model which utilized Newton's second law and took F-net to be equal to the weight force of -g times the mass of the object, where g is equal to 9.8 meters per second. I set the terminating condition of the while loop to be the final time from the experimental data, set W, which is here the weight force, equal to the F-net, generated a velocity iteration formula from Newton's second law, and then used that velocity in the position update formula to iteratively determine the new position of the ball at any given time t. Running the code, the effect of the weight force is clear, as the velocity of the ball appears to increase with time. Note that the length of the arrow which represents the vector weight force does not change, indicating that the magnitude and direction of the weight force is constant. Additionally, the shape of the graph appears to generally match that of the graph of the experimental data seen earlier. Plotting the model position versus time data from the CSV onto the same graph as the experimental data shows that our model did not provide a total fit. The model overpredicts the position of the cup in the latter half of the time period. This indicates that there was another force acting on our system, namely the drag force. To create a model which was a better fit for the motion of the falling cup, I included the drag force in my calculation of F-net, which would allow me to account for the overprediction of position, because the drag force points in the opposite direction of motion. To do so, the following changes were made to my original code. Leaving everything else the same about my code, I worked in a bottom-up manner, first adding the drag force Fd to my F-net, then defining the drag force to be a force whose direction is always opposite to the direction of the object's motion and whose magnitude is proportional to the square of the object's speed by setting Fd equal to a proportionality constant b times the magnitude of the cup's velocity squared times the direction vector j hat. I then used a guess and check method for different values of b until my final predicted position was very close to the experimental final position. I was able to get a final predicted position equal to 4 decimals to the experimental final position of -0.9478 meters, with a b value of 0.00625. Running the model, we can see the arrow representing drag force is at first not visible and then becomes longer as time progresses. This indicates that the magnitude of the drag force increases as the speed of the system increases. Plotting the data from this model and my experimental data on the same graph reveals that this second model was a much better fit. We can see the data points match up nearly exactly for the entire duration of the object's motion. Very slight discrepancies may be due to my own error when marking the point mass. We can now analyze the velocity versus time data for each model to determine if a terminal velocity was predicted. As mentioned earlier, the last time segment of the experimental data appeared to be trending towards a constant slope. A constant slope in the time versus position graph would indicate that the system had reached a constant or terminal velocity. When analyzing the velocity versus time data from the first model that took F-net to equal only the weight force, we can see that the slope is constant to the right, indicating that the velocity was constantly increasing and a terminal velocity was not predicted. Looking at the same graph of the data from the second model that took F-net to equal the weight force plus the drag force, we can see that the slope of the graph is decreasing and looks like it is beginning to approach a horizontal slope in the latter time segments, the same segments in which the experimental position versus time graph was approaching a constant slope. Though this model did not actually predict a terminal velocity, it appeared to be trending towards it and is likely that given a larger final time, the terminal velocity would have been predicted. If the cup was initially thrown downwards, say with an initial velocity of 4 meters per second, the cup would still have the same terminal velocity. it would just be reached earlier. By extending the time period to 2 seconds for our model which took F net equal to both weight and drag force, and plotting the velocity versus time, we can see that the terminal velocity is about negative 4.99 meters per second. By updating our code so that the initial velocity is negative 4 meters per second and plotting the velocity versus time data for the same 2-second period, we can see that the same terminal velocity is reached just a bit earlier as indicated by the black circle. In conclusion, by using Newton's second law and taking F net to equal the weight force plus drag force, I was able to accurately model the motion of an object falling somewhat slowly from rest.